Hi, welcome to a new lecture. Today we're going to talk about support vector machine algorithm or SVM. So SVM is a supervised learning technique or method that you can use either for classification or regression problems. The idea, uh, for example, in this figure is that we want to separate these two classes, right? We have like two different classes. So we set a decision boundary and we try to maximize this margin, right? That's going to separate the two classes. Now, if you notice, there are some points that are more active than others. For example, these red observations here and this, they are, that's what we call the support vector. These are the support vectors because they are, close to the border of the margin. So what the idea behind the SVM is that we want to find this margin area and the support vectors, and it focuses mainly in the support vectors because they are close to the border. So it's an efficient algorithm because it gives more importance to the support vectors than the rest of the observations. So that helps to generalize better the predictions. Okay, so the SVM technique, it tries to find a hyperplane to maximize the separation. This is for classification. In the case of regression, it's a little bit different. Now, the points that are close, we call them supervectors, right? Those that are close to the border. There are hard and soft margin classifications. In general, we will use soft, but let me show you the idea of the hard margin classification. So the idea is that we want to find a margin, like in this plot, where there are no points or observations inside the margin. This is like a street. You can consider this margin like a street. That's how the book call it. The book calls that margin like a street. So the idea is that the street is empty. There are no observations. So in the hard margin, some cases it's impossible here. For example, you have an outlier point here that belongs to this group. So it is impossible to find a margin here in this first block. In the second one, it is possible. But in general, it's difficult. If you have a lot of observations and you have no linearity, so it's complex. You need more flexibility. So in general, we will use soft margin classification. So we allow that there might be some observations inside the margin. That's possible because, again, if there are multiple observations that and given variability, that's possible. Of course, we want to reduce that, right? So there are some parameters for that. So this one, C, is the regularization parameter. So if C is small, so we have a wider margin. If it's greater C, then we have a narrower margin, as you can see here. Now we gotta be careful, right? Because I know that we in general we would like to reduce the margin, right? Or we want to avoid to have like multiple points here, but maybe we can cause some overfitting, right? So again, the same balance of variance and bias. In most of the cases, we won't be able to use linear SVM, and we will need to go to non-linear ideas, right, to fit the data for classification or regression. So there are different ways to approach this. So for instance, in this example, we're given this single variable x1, right, and we have like two classes here that we want to separate, and it's difficult to separate. But we can add more variables. Remember the polynomial filters that we use in the training models session. So for instance, we can use like a degree 2 polynomial, right, to create more filters. So we can add a second variable like x2, which is going to be equal to x1 squared, right? We increase the degree. So by having that additional variable x1 and x2, now please notice that the classes are separable. And that's like the core idea behind SVM, is to project the initial space into a higher dimensional space, so the separation is easier. That's the whole idea behind the support vector machine algorithm. Now, there are other alternatives. For example, we can use SVM kernels, especially when we're dealing with non-linearities. So there are different kernels, and they help us to perform a better classification. Now, sometimes they are called like a trick, the kernel's trick, because we can compute can project our initial observations into a transformed feature space, right? And that's important because we avoid the computational cost of adding new features. Remember with the polynomial degree, when you increase it to, let's say, 2, 3, 4, so that increases by a lot the number of features that you may have. So in the case of the kernel, that's not the case. So that makes SVM very flexible and complex for complex and nonlinear problems. So there are different types of kernels: linear kernel, polynomial kernel, and the most popular one will be the RBF when we have nonlinearities. So this is how it looks, the polynomial kernel. In the first plot, we have degree equal to 3, that's for the polynomial, and this one is degree equal to 10. So of course, in the degree equal to 10, you have like a better separation, right? You avoid some mistakes. But then you gotta be careful, because if you increase it too much, maybe you may experience some overfitting. So you will need to check, of course, the validation set, see the performance, how far it's from the, how big is the distance between the training and validation. So that's for the polynomial kernel. And the advantage here is, again, that you don't need to add the features, right, to create all the possible combinations that we explained in the previous video. And the Gaussian RBF kernel, so it uses a gamma hyperparameter, and this hyperparameter will help you with the bell shape for the separations. So again, this one is very reliable and robust when we have non-linearities. So typically practitioners will use this one first before the polynomial. Okay, so far we have talked about SVM for classification. Now, in regard to regression problems, the SVM, it has a similar structure. So now here we want to find the area or the margin that is going to include like most of the observations, right? It's going to include like a large number of observations with few of them outside this area. But same thing, you got to be careful with increasing it too much, right? Because we might have some maybe underfitting. So the balance, right? We need to find the balance with this hyperparameter, which we call epsilon. So if epsilon is small, so we have a small margin. And if epsilon increases, we will have a greater margin here. Okay, so in general, SVM, the idea of SVM is to find the maximum margin decision boundary based on support vectors, which, remember, these are the observations that are close to the border, right? So in general, they will be given more importance during the estimation for predictions and to define the margin. So it's very robust and effective on high dimensional spaces. When we have nonlinear scenarios, we can use the kernels. We can add features also. There are different ways to cope with this. And of course, it's really important to tune the hyperparameters. So we will have the C parameter. We will have also gamma, alpha, depending of the kernel, right? So this is what we call here the kernel parameters. So it's important to tune our algorithm to get better performance. Okay, that's everything for this video. I'll see you in our next lecture.